Hey everyone, welcome back to another Watch Me Do Math video. Now, I love this question. When I first did it, I thought it was great. It was similar to a kind of math question that I needed to learn how to do in order to understand what was really going on behind the physics I did, which was about a physical model of a bottle bobbing in the ocean with some drag forces accounted for. And that model sort of ended up in the form of a differential equation like this, but not as neat. It was in terms of physical constants and measurements rather than neat old numbers like in this pure mathematics question. But anyways, I don't know. I just personally found this question really nice. I don't think there's any particular reason that others would find it nice. It was just my emotional response to it. And anyways, I'm excited to share with you how to do this question so that if you had any difficulty, you can understand how to do it and be prepared to face similar questions in the future. So let's begin. We just deselect. Right. Using the substitution, z is dy over dx minus y, or otherwise, solve the equation d squared y over dx squared plus 2 dy over dx minus 3y equals 2 e to the x when y is 1 and dy of dx is equal to 2 when x is equal to 0. Now, what does this kind of look like? You may not have seen an equation like this before, but it is in fact something called a second-order linear differential equation. It's kind of like the quadratic of differential equations. And there's a reason I say it's like that. Because we're going to quote-unquote factorize it with the quote-unquote factor that we have been given. So this is not really the same thing that you do to a quadratic equation when you're trying to solve it for the unknown, but it just feels similar, and that's something I thought was really neat. That's one of the reasons I like this question so much. So suppose we have some z is dy over dx minus y. Say we wanted to just jam it into this equation here. What's the first place we could try and jam it? Well, we have some dy by dx. This is here. We have some dy over dx's minus y's in this equation here. We've got two of them, in fact. And then, apart from that, we've also got a minus y and a d squared y over dx squared. So one crude way we could go about this is just investigating this question a little bit, just playing around with the expression. We'd find d squared y over dx squared plus 2 dy over dx minus y equals 2 e to the x. And if we just wanted to get this z into the equation somehow, this is how we do it. So we'd get d squared y over dx squared minus y plus 2z equals 2 e to the x. But obviously that's not super duper helpful for us. So what else could we do? Well, one thing we could try and do is manipulate the expression on the left-hand side until it does fit in this form neatly. And one thing you can do is, similarly to how you might split up the middle factor of a quadratic equation into two pieces so it's easier to factorize, we're going to split up the middle factor of this differential equation so that it's easier to substitute our z equals dy over dx minus y into it. So in the same vein, we have 1 times minus 3. If you saw a quadratic equation, x squared plus 2x minus 3 equals something, and you wanted to factorize the left-hand side, you'd probably go about it sort of like x squared minus x plus 3x minus 3 is equal to whatever, because that's how you get similar looking factors on either side. You get x times x minus 1 here, and 3 times x minus 1 here. But when we do it with this equation, we're doing it with differentials rather than exponents, right? But the same principle still kind of applies. So y double prime plus 2y prime minus 3y is 2 e to the x. And so if we split 2y prime in the same way, we get y double prime plus minus y prime plus 3y prime minus 3y equals 2e to the x. And now let's write it out in full here. We get d squared y over dx squared minus dy by dx plus 3 dy by dx minus y equals 2e to the x. And this term can have a sort of dy over dx minus y quote-unquote factorized out of it if we acknowledge that this term is this differentiated with respect to x once. So it's like d by dx of dy over dx minus y plus 3 times dy over dx minus y equals 2e to the x. And I just think that's something really neat. Like, that idea of being able to manipulate a differential equation like that is just really nice. So if we substitute z in here, we get dz by dx, or dz by dx if you prefer, plus 3z equals 2e to the x. I'm gonna move the 3 to the dz over dx side, simply because that puts it in the form py prime plus y equals q, which is a form of differential equation that is easy to solve by using what is called an integrating factor. And it's sort of just a trick in the bag of tricks that you use to solve differential equations. And if you're not familiar with it, it's called integration by use of an integrating factor. And you can go research this yourself, because there are plenty of tutorials online that explain this better than I could off the top of my head. But anyways, the idea here is to recognize that this kind of looks like what you'd get in the product rule if you had some e to the whatever the integral of p is differentiated with respect to x. Because on the one hand, you'd have y e to the integral of p dx plus, because you're differentiating one of the factors, y prime e to the integral of this. Oh, actually, no, this is already in the form we want. So it's y prime plus py is q. Hang on, I may be confusing myself here. Nah, I think this is the right way. So if you differentiate something that looks like this with respect to x, you'll get y prime is e to the this on one side plus y times whatever this is differentiated. So if u is in the integral of p, then e to the u differentiated is just e to the u times du by dx, right? But du by dx is this integral differentiated, which is just p. So it's y times p times e to the root p dx is e to the root p dx times q. And this q is our 2e to the x, this y is z, this y prime is dz by dx, and this p is just the number 3. P could be any function. It's quite a generalized technique. But anyways, once we have it in this form, which I could rewrite out now as z prime e to the integral of 3 dx plus z times 3 times e to the integral of 3 dx, where we take the constant integration here as 0 just to make things a bit simpler, equals 3 times e times the integral of 3 dx times 2 e to the x, which is e to the 3x 2 e to the x. This is z 3 e to the 3x, and this is z prime e to the 3x. If we integrate both sides of this, we have 2e to the 4x on one side, and in the same way that I suggested before, we have e to the 3x times z on this side. So say we integrate it this way. You may be hearing some car alarms outside my window. This is because I live nearby a motorway. We have some boundary conditions. Y is 1 and dy by dx is 2 when x is equal to 0. Let's just figure those out later. 2 e to the 4x goes to 1 over 2 e to the 4x plus some c. E to the 3x, z is that. So if we divide by e to the 3x, we get z is half e to the x plus c e to the minus 3x. So what is z? Well, if we substitute dy by dx back in, we get an easier differential equation in terms of y. And it's kind of like we've done two differential equations in one question. So if y prime minus y is this thing here, and again, it's in this form, something y plus py is this, where p in this case is negative 1. We can multiply by e to the minus 1, integral of minus 1 with respect to x. Let me just drink some water again, because I've made 3 of these videos in a row or something. E to the minus 1 dx is our integrating factor that we want to multiply everything by, or e to the minus x. Y prime e to the minus x minus e to the x y is 1/2 plus c e to the minus 4x. This gets us d by dx of y prime, of y e to the minus x is 1/2 plus c e to the minus 4x. Good God. Are there any more conditions? I feel like we need... Oh, never mind. Y is 1 and dy by dx is 2 when x is 0. So first we're going to find out what c is using the information that I've just looked up from the question. So y is 1 and dy by dx is 2 when x is 0. This gets us 2 times 0 minus 2 times 1, because it's e to the 0, minus 1 times 1 equals 1/2 plus c times 1. Or rather, 1 is 1/2 plus c, or c is 1/2. We now know that if c is 1/2, this is sort of 1/2, 1 plus e to the minus 4x. So therefore, d over dx y e to the minus x is 1/2, 1 plus 4 e to the minus x. Integrating both sides, we get y e to the minus x is equal to 1/2 of x minus 4 e to the minus x plus some c, as y is 1 when x is 0. Let me just check that those are the right values, actually. Yep. As y is 1 when x is equal to 0, we find that... I don't know how the zooming on this thing works. We find that 1 times e to the 0 is 1 is 1/2 times 0 minus 4 times 1 e to the 0 is 1 plus c, or rather 1 is minus 4 over 2 plus c, 1 is minus 2 plus c, c is 3 in this scenario. And so we get y e to the minus x is 1/2 x minus 4e minus x plus 3. And if we are to multiply both sides by e to the x to get an expression for y in terms of x, the grand finale of solving any differential equation, isolating y, we get y is equal to 1/2 x e to the x minus 2, because that's what 4 times e to the minus x times e to the plus x, those two exponential functions cancel out, and then minus 4 over 2 is just 2, minus 2, plus 3 e to the x. And that's all. So y is 1/2 x plus 3 e to the x minus 2. And I believe that's it for this question. So hopefully you found that as interesting as I did. If it's something you like, if it's a kind of question that you thought was pretty beautiful, like I thought as well, then be sure to leave a comment. Let me know if you did enjoy it. And I apologize if the quality of this video is not so good as the other two-step questions, because I've recorded them one after another. But hopefully I was able to fairly clearly explain what to do in this question. And if you want any more pointers on how to solve this kind of question, then be sure to look up yourself integration by use of an integrating factor. Very useful technique, very fun technique. And until next time, hopefully this answer is correct. I'm not fully sure. Again, I am prone to human error. Thank you for watching.